Good evening. We are going into the next session of our chapter, Work Energy Power. In the last session, we were discussing about the gravitational potential energy, and today we have the potential energy of a spring. Okay. What we've drawn here is, you will see that this is a horizontal surface on which we have a block of mass m, and I have connected, there's a wall here, and to the wall we have a spring which is attached to that block of mass m. Now, in its initial position, a free equilibrium position, we have marked that x equal to 0. I may apply a force Fa, applied force, and displace it to the right to a maximum displacement xm, and that's what I've shown here. Now, you will notice that if you have a spring that is attached to a wall and you try to pull it to the right, as you pull it to the right, initially it'll be easier, but as you start pulling it, you will see that this spring force will exert an opposing force, and because of that it becomes harder to pull as the displacement goes on increasing. So you see that this spring force, actually when you're trying to displace it to the right, the spring force will be to the left, and also as the displacement increases, the spring force also goes on increasing because you're finding it harder to pull. Same way, if you push this block inwards, you will see that the spring force is opposing that. And not only that, as you start, it may be easy, but greater the displacement, more difficult will it be to push it in. So that means you have spring force, two properties. One, it's always opposite to the displacement. Second, it is a variable force, meaning it increases with displacement. So combining the two, you may write Fs is directly proportional to minus x, showing you that the spring force is proportional to the displacement. Also, it is opposite to the displacement. Or you may write Fs is equal to minus kx. And this is called the Hooke's law, or it's also called the Hooke's law, or it's also called the force law. Okay. Now, this constant is called the spring constant, which is, for a very stiff spring it will be large, and for a soft spring it will be smaller. So, this K, the spring constant, is actually Fs by x. So, its SI unit is going to be Newton per meter. Right. So, and you're going to see that the spring force is a variable force. Also, it is a conservative force. We'll prove that towards the end of the session. Now, what we're going to do next is to find out the potential energy of the spring, potential energy of a spring. See, remember I told you in the last session, when we lift up a body, you are actually doing work. The external agency is doing work against the gravitational force, and that work done is stored as the potential energy. So here also, if you try to displace the block to the right, you have to do work against the spring force, and that work done will be stored as the potential energy. Now we cannot, so we now know we are going, work done by the the spring force is going to be negative because forces in this direction, displacement is to the right, and there is a 180-degree angle between the two. So we have F d cos theta, or in our case the displacement is x and this is Fs. Because Fs and x are opposite in direction, this will be 180, and cos 180, you are going to get a negative work done. So we are going to see that you're going to get a negative work done. Now you cannot simply say work done as Fs into x into cos 180 as minus, because this force is not a constant throughout the whole displacement. We just saw it's a variable force. It goes on increasing with displacement. So you cannot simply multiply Fs with the total displacement xm, simply because during this displacement at each interval the force is going on increasing. So then what we'll do is we'll divide that total interval, that is starting from here till here, we will divide it into very small intervals of dx, and because dx is an infinitely small interval, you may assume that in that interval force is a constant. And then we find the small work done in that small interval using the formula f dx, and then integrate from 0 to xm. Okay. So that small work done you may write as Fs into dx, which is minus kx into dx. And the total work done, you have to integrate dw, which means you have to integrate minus kx dx starting from 0 to position xn, 0 to position xn. So this is, I'm going to take this minus k outside, 0 to xm x dx. I hope you remember, I've already taught you integral x raised to n dx is x raised to n plus 1 by n plus 1, or integral x dx will be x raised to 2 by 2. So we have here minus x after integration, this is x squared by 2, limit 0 to xn. So this is minus k into, this x will first take the upper limit. So this will become xn square by 2 minus 0. Or you see, like I told you, we are going to get negative work done. So that is work done is equal to minus half k xn square. This is the work done by the spring force. And the work done by the external agency against the spring force is stored as the potential energy. So potential energy V is going to be plus half k xn square. Okay. So this is how we get the potential energy expression. Now next I'm going to show you that you can arrive at the same formula for work done by a graphical method. Now if you draw the graph between the spring force and displacement. So we have a graphical representation. We take x here and fs along this. Now because fs is equal to minus kx, you know you're going to get a straight line because this fs is directly proportional to x. Directly proportional meaning you're going to get a straight line. Now also this graph can, the straight line can only be in the second quadrant and the fourth quadrant, because here both f and x have to be positive, here both f and x have to be negative, which cannot be, because if f is positive, x is negative. If f is negative, x has to be positive. So our graph will be like this, okay, and this graph will be the fs is equal to minus kx graph. Now if you take the area here, area of this triangle, where this is the maximum displacement, let me call the triangle OAB. Let's find the area of that triangle. So area of triangle OAB will be half into base. Base is xm into, this will be the force Fs, because this is a force axis. Fs, which is half into xm into minus k. If the x is xm, then this is. So minus half k xm square. This is what we got as work done by the spring force, and this is what we are getting here also. So we can get the work done by the graphical method by finding out the area under the graph for the spring force versus displacement graph. Okay. Now next what we are going to do is to show that this is a conservative force, that spring force is a conservative force. In our last session we discussed three properties of the spring force. First one, I said that if the force is a conservative force, it can be expressed as the negative of the derivative of potential, a scalar quantity, that is potential in our case. Let's check that. That's minus d by dx of potential energy I just showed you is half k x square. X, I wrote xn because that we took the maximum displacement xn. So this is going to be minus half k, I take outside because it's a constant, d by dx of x square. Now d by dx of x raised to n is n into x raised to n minus 1. So d by dx of x raised to 2 will be 2 into x raised to 1. So this is minus half k into 2x, which is minus kx. So we got this as a spring force, right? We know that Fs is minus kx. So we have shown that this spring force can be expressed as the negative of the derivative of potential. in which case we know that this spring force is a conservative force. Now the second property we discussed about conservative forces are that they are path independent. They do not depend on the path taken, the work done. The work done depends only on the initial and final position. So let's imagine that we are now going to move the block from xi to xf. Okay. So I'm going to find the work done in this interval. For that, I will first divide it into small interval and find out the work done in that small interval as fs into dx, because I know that in this small interval the force can be taken to be a constant. So this is minus kx into dx, because fs we know is minus kx, Hooke's law. So to find the total work done, I will integrate dw, that is I'll take minus k outside, integrate x dx from starting from this position xi to xf. This is minus k. I just showed you that integral x dx is x square by 2. So x square by 2 starting from xi to xf, that is minus k. First this will take the upper limit, so xf square by 2, then I'll put the negative outside, then minus k into, it will take the lower limit then, so xi square by 2, or we know that the work done now is equal to k xi square by 2 minus k xf square by 2. I took the negative inside, so positive k xi square by 2 minus k xf square by 2. So you see, the work done is independent of the path taken. It depends only on the initial position and the final position. Suppose you took the block from, let's say it was initially at xi, pulled it to xm, and then brought it back here. So you first pulled it from here and then brought it back here. But we don't care about the path taken. The work done will depend only on this and this, independent of where you took it. So that is why, so the next property, that is spring force is a conservative force, because you see that the work done is independent of the path taken. The third property we discussed was that the if it's a conservative force, then work done in a closed path has to be 0. So let's say we took the block from xi, took it up to xf, and brought it finally back to xi itself, closed path. So then this will also be xi, right? So work done will be 0. So you see, if you take it from here, take it up to here and bring it back, that is a closed path, work done is 0, and further showing you that this spring force is a conservative force. Okay. Now the last thing I want to show you today before I end this session is the graphical representation of the variation of the energy of associated with the spring. Okay. So we have, I'm going to on the horizontal axis the displacement, and here I'm going to plot the energy. Now we know that the potential energy is given by half kx square in the case of a spring, and the kinetic energy should be half mv square, where m is the mass of the block. Now at the equilibrium position here, x equal to 0, this is xm and this is minus xm. Okay. At x equal to 0, you know this x will become 0. So potential energy will be 0. And at maximum position here, let's say this is the xm. Okay. At the maximum position, you know that this x here, this x is going to be maximum. So potential energy is going to be maximum at xm. So at xm we have maximum potential energy. Minus xm also you will have maximum, because x is squared, right? So you will have maximum potential energy here also. So you will see the potential energy curve looks like this. Okay. Minimum value of potential energy at equilibrium position. Now when you go to kinetic energy, you see that, see here you have pulled the block up to here and you are leaving it. So it is now at the point of return, and at the point of return we know v is going to be equal to 0. Just like you would throw a ball up and its maximum height, at the point of return you know the velocity will be 0. Same way, if you pull your block to the right and leave it, at the point of return V will be 0. Similarly, if you displace it to here and leave it, this is going to come up to here and then return. So here also V is 0. So at both extremes, we have the kinetic energy 0. So this graph is for the potential energy. So here at both extremes you have kinetic energy 0, and you know as it oscillates at this position velocity is going to be maximum. So at x equal to 0 we have maximum kinetic energy. So the dotted curve is for the kinetic energy, but at any position the total mechanical energy K plus V equal to a constant. Since we have a spring force as a conservative force, the total mechanical energy will remain a constant. We did that in the last session where we said if the force acting on a body on a system is conservative, then the total mechanical energy is always a constant. So that this will be the total energy, that is K plus V given by this dotted line. Okay. So this is what we had to do today. Potential energy of a spring, you need to find the work done graphically and otherwise, and also show that the spring force is a conservative force. Thank you and good night.